So up until this point, we've gotten to be, I hope that you've gotten to be, I feel like we've talked quite a bit about analyzing motion. And we've been analyzing motion between objects that are either independent or connected objects. We've looked at connected things, objects that are connected by some rigid cord or something like that. But in either case, these are sort of isolated. We look at connected objects as sort of an isolated system. And we haven't really looked at what happens when two seemingly independent objects interact in the same sort of sequence of events. So the question is, what about objects independent objects that aren't connected? And really what, this sort of what we're talking about here are, basically collisions. And not necessarily collisions, involving two cars on the highway, really energetic, really exciting collisions, but just, objects that are bumping into each other and interacting with each other. Okay, so just generally, any two objects that start out independent and then encounter each other and then are affected because of their encounter. So in this sort of scenario, looking at energy in the system, looking at the total energy of the system, looking at the individual energies of the objects in the system isn't enough to really tell you about the motion of the two objects, or three objects, or however many objects that you want. For example, so energy and it's not to say energy doesn't always work. Like looking at conservation of energy problems, tracking energy. Not to say that we can't use those ideas, but like I've been saying over the past several days, we just don't have the ability to track different types of energy. We can't track the energy that goes into heat at this point. We can't track the energy that goes into crumpling some device and deforming some device. So I'm quantifying this as saying when we have objects that crumple or deform, we don't have the ability to track the losses of energy in this system, where the energy goes. Similarly, if we have objects that stick together, we don't really have the tools yet to understand the motion of those sorts of objects as they interact. So we need another quantity that allows us to do these sorts of things. And that quantity is going to be linear momentum. So we're going to start out talking about linear momentum, and I'm going to just jump right in and give you the physical relationship. Linear momentum gets the lowercase letter p, and it's equal to the quantity mass of an object times its velocity. And I will note right now that this is a vector. All right? It's very important that you remember that's a vector, because we've sort of gotten in the habit now of dealing with energy, which is a scalar. And momentum and energy, often the equations for momentum and in particular kinetic energy look very similar. They're both dependent on mass and velocity as just a 1/2 in kinetic energy and a v squared. Okay, but the v in the kinetic energy term is a scalar. We're talking about the speed. Now we're talking about the vector velocity. To get it out of the way are units that you should become familiar with when you're dealing with momentum. The units of mass times the units of velocity, which is a kilogram meter per second. And there is no special name for our momentum units. It's just kilogram meter per second. So before we get into it, I want to just talk about, yes, this looks very similar to kinetic energy, but it's not the same. And a good way to look at this is when we first started talking about kinetic energy, we talked about, we compared a bullet and a baseball. And we said that the bullet had a larger kinetic energy than the baseball. But if you do the same calculation using the same types of values, you would find that the momentum of the bullet is actually less than the momentum of the baseball. Why do you suppose that is mathematically? Yeah, I mean, so the difference is in the speed or the velocity. We don't have a squared term. So the bullet, while it's very, very light, it's moving at a pretty high speed, and you're squaring that speed. So mathematically speaking, there's clearly a difference. And that shows up in the quantities in the examples that we'll encounter. So it's not just a mathematical thing. It's really a different concept. Momentum is a completely different thing from kinetic energy. And you sort of have to recognize that now because you're going to be using the two together as we move forward through our discussions with momentum and then ultimately into collision. Okay? So let's talk a little bit about the key idea behind momentum. And that relates to how momentum and forces are related. So if you can think about the only way to change an object's momentum. So if we want to change an object's momentum, we either have to change the object's mass or we have to change the object's speed. Now, we haven't really talked about changing an object's mass. Every problem we've done in this class has been a constant mass. But we certainly have talked about changing an object's speed. What do I mean when I change an object's speed? Acceleration. The object's accelerating. So in order to make an object accelerate, I have to do what? You have to apply a force. So there's this really intimate relationship between momentum and forces. And that's sort of the cornerstone of why we even get into momentum in the first place. But let's take a look at this graphically first. So imagine that you have some mass cruising along at some speed vi, v initial. And you apply a force to that object. I don't know how I do that. It's magic. So I apply a force to that object in the same direction as the object's moving initially. So a bit later then, I look at, it's not the color I wanted red. So a bit later, I look at my object again, and now it has a larger speed. And I apply the force, I cause the object to accelerate, its speed is increased. I've changed the object's momentum. So I can say that the magnitude of the final momentum is larger than the magnitude of the initial momentum. All right, nothing all too surprising there. By applying a force, I've changed the momentum. Similar mass, similar initial velocity. Object's going to accelerate perpendicular to its trajectory. Is my momentum going to change in this case? Okay. So the first thing that should give it away is that momentum is a vector. Anything that's a vector, that means that direction is important. So it doesn't matter that I'm applying a force perpendicular, my momentum will change. At some later time, I'll have a v final over here, and we could make the claim that, sure, I could set this problem up such that the magnitudes of the speeds or the velocities are the same, The speeds are the same, but the angles are not. The direction of my momentum has changed, which means then that the actual vector is not the same. So the final momentum is not equal to the initial momentum. Right? Direction's important. Just like I wouldn't say a force of 20 newtons to the right is the same as 20 newtons up. Those two forces may be the same in magnitude, but they'll cause different accelerations. Okay, so direction is important. Now, there's something missing here, though. If you think about how to change the momentum of an object, you can sort of think about two different ways to do it. Right, so in my picture up here, I'm applying a force and over to some mass with an initial velocity. If I just apply this force for a split second, a tenth of a second, really, really short time period. So I'm going to sort of do an extension here. Really short, really quickly, I apply a force. Well, then my momentum isn't going to change very much. It's going to change a little bit. So this is now V final. Okay? But if I do something else and I say, well, I'm going to apply that force for a long time, so a long force, well, then my velocity, that could change pretty significantly. The direction could change pretty significantly. So what I'm getting at here is that not only when I'm looking at momentum, not only is it important to take into consideration the force, it's also necessary to take into account how long I applied that force. So if I apply a big force for a short time, that's the same as applying a small force for a long time. As far as momentum is concerned, as far as your change in velocity is concerned. So in the example realm, you can imagine, what sort of scenario in real life do you apply a big force for a short time? Hitting a baseball? I don't know about lifting something. I don't know. It's sort of a medium amount of time. Sure. I mean, it's all relative, right? I think about hitting a baseball, I don't know, golf, baseball, something like that. Really quick impact, very short delta T. Very big force, ball goes a long way. The examples of applying small forces for a long time, I can think of really small forces. We talked about at the beginning of the semester an ion drive as a mechanism to propel a spacecraft. Really small forces, but if you do it for a long time, you get big changes in your speed. So those are a couple just examples that come to mind when thinking about this sort of idea of two ways to change momentum. So with that sort of conceptual idea, we could come up with an equation, right? So we could talk about a new equation. So in fact, this equation is really pretty important, and it's actually what we're going to do here is we're going to rewrite Newton's second law. So this is another way to express Newton's second law. Now, Newton's second law told us that if you add up all the forces acting on an object, well, that was equal to the mass times acceleration. But we just talked about, well, if you have a force acting on an object, depending on how long you exert that force for, you change the object's momentum. So writing that mathematically looks something like this. If you have a net force acting on an object, and then you're exerting that force over some time period, then you must change the momentum. So of course, we typically write this as delta P is equal to this net force acting on an object. I'm just going to write F net. And again, this is a vector times some time interval. And this quantity is pretty important. This quantity is called the impulse. So we give it a special letter, a capital I. All right? If you have a net force acting on an object for some amount of time, that's an impulse, and it's equal to the change in momentum of that object. So I like to associate this with a graph. So you could even think about the example of the golf ball that I just mentioned. So you can imagine that if you're hitting a golf ball and you plotted the amount of force that you were exerting on that golf ball as a function of time, what might it look like? I envision it looking something sort of like this. You start off with no force, and then you just contact it, and pretty quickly the force acting on that ball goes upwards. Now we're talking a really short amount of time here. And then at some point there's some maximal force, and then slowly that starts to kind of come back down, and maybe the profile looks like this. Okay? Now, the important thing to recognize is when we've been talking about forces so far in this course, we've been talking about how a force causes an acceleration. So if I want to look at the acceleration of the ball, I sort of have to look at the acceleration at every single instant in time. I need to look at the instantaneous force. This force is changing throughout time. And one of the things that we haven't really talked about in this course is, all the forces we've dealt with, for the most part, have been constant. Now, we talked about springs, and those have been non-constant forces, but we had a nice little neat equation, 1/2 k, or not, I'm sorry, kx force through the spring. We can solve for that. Not really all that interesting. But, most things in life don't have nice constant forces. The forces either off or on. Most things have some shape. You interact, two cars interact. You walk on the ground and exert a force on the ground. It's not a nice little flat line. Force and then apply Newton's second law, F equals ma, to figure out the acceleration. But that doesn't really make sense, because what are we really after when we're talking about forces and accelerations? We're just trying to solve for the motion of an object. We care about the velocity. We care about the position. Understanding the force, understanding the acceleration is just sort of like a means to get us to figure out what the velocity of the object is, what the final position of the object is. So the nice thing about momentum is that we're sort of ignoring what's happening during the collision. All we really care about is, okay, if I want to know what my velocity is going to be in a little while, assuming that some force is going to have some effect on me, I don't really care about all the details about the force. I just care about how long it's acting and sort of what a representative value of that force is. So because of this sort of idea right here, I can rewrite this in a different way. I could draw a picture that says, well, it doesn't really matter about the details of the force. If I know how long the force is exerted for, and I just call this some average force, if I take F average and multiply that by delta t and call that my impulse, then it's going to tell me the change momentum. And what is this number? What is force average times delta t? Well, force average is the height of this rectangle. Delta t is the width of this rectangle, so that value is that's just the area of this rectangle. Right? So that's exactly the same thing. What I'm really after is, when I'm calculating the change in momentum, I just care about the area under the force versus time curve. In other words, I care about the integral of the force. Now, of course, I can't say that in this course, but that's really what we're looking at. And so the whole point of that is, I don't really care about the details of the force. It doesn't matter how the force is changing with time. As long as I know what the average force is, how long it's been acting for, then I can calculate my change in velocity, which is the thing that I'm usually really interested in anyway. So that's sort of the power of this whole equation right here, this other way of writing Newton's second law. And there's one other thing that you get out of this that you might sort of draw a parallel with what we've been doing already. So right now we have this new thing. We have, or let me go back. Let's go back to last week. We had an equation that looked something like this: F net times delta x. All right, that's equal. This is work, right? Force over a distance. That's just work, and so that's got to be equal to some change in energy. This was the work-energy theorem. This gave us a way to relate the change in, quantities that we're interested in, speeds, positions, all right, to some force. Again, we didn't really care about the details of the force because we were looking at sort of the before and after picture. Well, now we have a very similar equation that says that F net times delta t is equal to delta p. The only difference is I stick a couple of half arrows on top of my letters because they're vectors. And now we've defined something that's called the impulse momentum theorem. And this is basically doing the same thing. It's giving us a way to figure out how the variables that we're really interested in when we're talking about motion, namely velocity, how that's changing without really taking into account any of the details that are happening while the change is happening, while that force is being exerted. And we could use this to solve some pretty interesting problems. And so that's what we're going to spend the next day and a half doing.